Okay, welcome back everyone. Last day, we gained an understanding of steel industries. Continuing with the series, the session is about the cement industries. Our speaker for the session is Mr. Umesh Shrivastava, Head, Operation and Maintenance, Ultratech Cement, and one of the most adored alumni of GC Bilaspur from 1992 batch of mechanical engineering. After completing his masters, after completing his bachelor's, he joined the cement manufacturing unit of AICTE Birla Group in the year 1994, and at present working as head of operation and maintenance and safety and sustainability of Ultratech Cement. He worked in areas like projects maintenance, general management, research and development, safety and sustainability with expertise in Six Sigma, business excellence and research and development. He was climate change task force in the year 2007 and also represented Indian cement industry in the United Nations Climate Change Conference in Bali in the same year.
So it's my privilege to address all of you, and I would like to share something little which I know about the industry in which I am working. So my knowledge is primarily from the applied point of view. So I was listening to the part of the lecture of Dr. Hari Prasad earlier. So let me take you through my industry. I would like to share the slides here. Is it visible now?
Yes.
Yes, sir. Yes, sir, it's visible.
Slides are visible. Very good. So, friends, I am just talking to you about the world of cement, and if we just know that in last say 2-3 centuries, what the Earth has become. So, what is the biggest change which has taken the change of the shape of the human habitat, or I would say the way we are living, the way we are doing the work. So cement is one of the important aspects which has come in the human life, and the places where we live, so the houses, the roads, the bridges, the dams, the industry itself, they all consume cement, and cement is one of the important metrics of the development of the country. When we say this country is a developing country or this country is a developed country, some or the other wise, is my voice audible? Because I'm getting one bad network quality type of message here.
It's it's quite clear, sir.
Okay.
It might be possible you get some glitches, but it's clear.
Okay, right. So, what? So cement consumption is actually a mark of that how the country is progressing. And when we see the cement consumption of very developed nations like Europe and America, we see that historically they have consumed a lot of cement, say from the beginning of the 19th or 20th century. So almost for the century, they have consumed a lot of cement. They have developed their industries, their roads, their infrastructure brilliantly. So now their consumption has come to a plateau level, while the countries like India, Indonesia, even Vietnam, if you see, or China, China is a giant, and China is consuming a lot of cement. So as we go forward, I will try to bring those dimensions to you. So let us talk about that, how the cement has come to our life. So there was a gentleman called John Smeaton. So he was an engineer, and his responsibility was to put up a Eddystone lighthouse, which was which was located somewhere in the southwest of the England. So while he was doing that, he found lives. So I will just give you some idea about the cement capacities of the world. So these are the charts. So while you see the China on the top, the China consumes more than 50% of the total world cement, and their capacities is around 2200 to 2500 million ton. Now this, but at the same time, China is not very transparent in, I would say, getting the data. So the world actually do not know how those 2500 tons or 2200 tons and how those figures are moving. Means whether consumption is going down or going up. It is believed that the consumption from last few years have dropped significantly. Something like 7 to 800 might have dropped. This is what the statisticians feel. But still, that number is very high. The second is India. Today, Indian cement industry is hovering around, say, 300 to 350 million ton. We have that kind of capacity, and we are producing around 300, around, I'm touching something like 300 tons. We are still having a latent capacity. I will say that when we talk about 350 tons, and we are producing 300 tons, so there is a gap of 50 million ton. But this gap is even more because there are means and methods by which we can uh, add back and improve the volumes. So India lies the second, but you see the large gap between India and China. Then Vietnam, which is again a small country, it has come as in last decade. It has picked up the demand, and then United States, then Egypt, and Indonesia, Iran, Russia, Brazil, Korea, Japan. So some or the other way, this is actually uh, important metrics which also measures that how the country is developing. I will say that cement and steel both are those important metrics, and cement also is very important for socio-economic condition of the nation because it is the largest employer, one of the largest employer. If you see the size of the construction labor or construction workers we have, so it is one of the largest employer. That's the reason government always, say, while making the policy, they take a lot of care about this sector. Next. So now, when I joined cement industry in the year '94, that time what I learned that time we were around 80 million tons capacity. India was having a capacity of 80 million ton, and 100 million ton was a aspiring target that we will be reaching 100 million tons shortly. So, and what we used to hear from the experts in those days, that India has abundant reserves of limestone, abundant reserves. We just don't have to we don't have to worry about it during our lifetime. We have such a huge reserves everywhere. There is limestone, and we can put a lot of cement plants. It's all about the demand, because the demand is at the moment the demand picks up, we will just have to just add on the plants, and we can jack up the demand. That was the thought. And there is a distinct pattern if you see in the cement manufacturing capacity. These are the clusters. Because the limestone reserves, which is
concrete or highway किसके
hello.
Sorry for the glitch, sir. You may continue. I am muted.
Okay. So if you see, there are certain clusters in which we have got very good limestone reserves, and most of the cement industry is concentrated in those clusters. So if you see from the west side, there is a Junagadh cluster. So there is a lot of cement plants in this area, in the southern part of the Gujarat. And then there is a Chanderiya cluster, which is in Rajasthan. and part of MP also falls in that. And there is a Satna clusters, which is somewhere in the northern part of MP, closer to UP and Bihar. Then Bilaspur cluster, where we have got a lot of cement plants, big capacities in Bilaspur cluster. In fact, Chhattisgarh is the state which is the largest exporter of the cement. And if you see, our eastern side does not have very significant reserves. Though while we are talking about the clusters, there are still some of the cement plants which exist out of the clusters. But I will say that something that 80-20 ratio works here. 80 to 90% of the plants falls in the cluster, while 10 to 15% plants are out of the clusters. So you see that the whole eastern, area, they do not have any significant limestone. So they all depend on the Bilaspur cluster. So Bilaspur supplies the cement to the eastern part of the country, and then there is a Nalgonda cluster, Yaraguntla cluster. Then there is a Gulbarga cluster, which is in Karnataka. Then there is a Chandrapur cluster in Maharashtra, and then there is a south. There is a Aryalur cluster, and as so you will see that there are some gaps. Like in the northern India, you will not see any significant clusters. So these are always away from the primary markets. Then similarly, this southern area, so they all depend on the, say, Kerala completely depends on the Aryalur clusters, or there are some cement which is coming from the coastal route from Gujarat to the coastal belt, basically. So it also reaches to Kerala. Fortunately, I'm in a company which has got plants in almost all the clusters, and we also have got some plants out of the clusters also. And most of the clusters I have visited during my professional life. So and this is about it. I want to also mention one more thing, that cement, wherever we want to put a cement plant, the limestone reserves necessary has to be there, and limestone is alkaline in nature. So because of the alkalinity, you generally see the topsoil will not be very fertile. This is a this is a thumb rule. Most of the alkaline soils will not be very fertile. So typically in all these areas, these were typically the backward areas where there was a low vegetation, the per capita income of the peasants were very low, you know. So this somehow gelled very good with this thing, because putting up a cement plants means you have to acquire a very big size of land, and these days with all these arms and restrictions, it is not so easy to acquire this big parcels of land. So this was this phenomena worked very well for the cement industry, that uh, where the people required a job or needed a job where the fertility was actually low, there the cement plant was coming. So that become what to say, that a kind of good balance for the people who are dwelling there, and it was a win-win situation for both the things. So this is about the cement clusters in India. Then I would like to take you to this, when we want to put new plants, what are the major aspects which should be considered. Certainly the limestone reserves, it should at least last for 50 years. If I have to summarize the business of cement, I will say it is the business of logistics, because the limestone which will be converted into cement, and then this cement will be going to the various locations where it will be converted to concrete, and then concrete um, will form a shape of, it can be forming a shape of your house, it can be forming a shape of a bridge, or a dam, or various civil structures. So it is all about the logistics, I will say. So looking into that thing, it is always economical for a cement plant to put a plant exactly there where there is a huge limestone reserves, or exactly over the mines, so that you can have a minimal limestone logistics cost. And the thumb rule equations goes like this, that to make 1 ton of cement, you have to burn around 1.5 tons of limestone. But while you take 1.5 tons of limestone, typically you also handle around 0.5 to 1 million ton of the topsoil and other materials which are in the mines. So the kind of the material handling this industry is doing is enormous, and I would say humongous numbers will come. We have a lot of when we talk about the mines, there is a lot of heavy earth moving equipments which are put to use, and cement industry is also industry which has all the aspects of the engineering and whatever the knowledge we have, that is all used um, to make this industry live. So second important thing is the coal sources. So the limestone has to be there, and if I just see the thumb rule, so the second biggest raw material is the coal, and the percentage of coal generally varies from 8 to 10% depending on the calorific value of the coal. I would say higher the better the quality of coal, you may require less in uh, quantity, I will say. Okay, so coal sources, the more it is nearer, you will incur less cost. Third is environmental considerations. This is very, very important, because the moment we talk about putting up a plant, it occupies something like 30-40,000 acres of land. If we translate it, it is like multiple kilometers of the land, multiple square kilometers of the land. And you have to displace people. If they have a villages which is sitting on some mines, then they have to be displaced. They have to be displaced in such a way that minimal damages are happening. And what is the quality of limestone, how which quality band is where, how are we planning to use the limestone for say next 30, 40, 50 years. We have to have a very long term plan before starting a mines. And then, is there a forest, is there a vegetations, so we have to take care of all those things. No, you cannot do anything with the forest. Even if there is a wild uh, this if wild animals are also around, you have to take care of that. There are some plants which has to change their plan drastically, because they were falling in the line of the wild animal passage, like the elephant. Uh, it was coming on the pathway of that, so they have to totally abandon those mines. And so environment considerations are very, very important. Then out of all the things which I'm telling, there is one very positive thing about cement industry, that it also consumes the waste of the other industry, like fly ash from the power plants and slag from the steel plants. So these sources are also important, because while to convert a limestone into the cement or the clinker in between and then to cement, we require coal, and it's a very critical process from which the limestone has to go in, and it incurs a lot of cost. While fly ash and slag, they are very close. Their properties are very close to that of cement. So with a small augmentation, these things can be used in cement. So there's a reason. It's a very healthy win-win situation for cement industry and the other industry. They can coexist with fly ash and slag uh, sources nearby. Certainly, for any industry, the market proximity is important. So this is with the cement industry also. With the clustering, you will also see, because there are clusters, so there are areas where there is a lot of supplies of cement, so the prices there are not so good. While if you go a little away, maybe 500 kilometers, you see that there may be a shortage, and So the closer to primary market is very important aspect here. And then road and rail infrastructure, because when we talk about cement manufacturing, we are also talking about a huge movement of material. So we require a road and rail infrastructure, a very good road and rail infrastructure, which is like having a continuously dedicated um, um, railways are there. So these are some of the aspects which we consider for the new plants. Now, I would like to take you through the cement manufacturing technology, which has evolved from the older days, like from the early 18th century. So initially, the cement plants were the wet process plants. So if in a nutshell I have to explain to any layman that what is cement and how cement is made, I will simply say that we have to take out the limestone, which has a fair amount of lime in it. It has to be grounded to a powder. Okay, then that powder has to be heated uh, to a very high degree, something like 1400 degree, 1500 degree Celsius. At that temperature, this that powdered limestone fuses and it forms a clinker, and that clinker is actually uh, the intermediate block of the cement. Now that clinker is further grinded to make the cement. So the whole process you will see it's all about grinding, heating, and again grinding, and maybe mixing and then transportation. So so during the wet process plants, in those days, the grinding, the dry grinding was not very much possible. And similarly, the heating also requires a lot of moisture to, I would say, make the material flow or make the material bind to some extent, and then you know. So that's how this wet process plant was there, but it was using excessive heat. Today, it is actually not economical for anyone to make cement through the wet process plants. All the wet process plants are totally closed, and running a wet process plants means you are at least using double the cost, double the coal, at least double the coal, double the double the quantity of coal what you are using now. You have to have, because you have to make that moisture which you have added from grinding to evaporate. So after that, the dry process technology has come, where heat recuperation means I will take you through those aspects also. Then dry process was somewhere like up to 1 million ton plant were a dry process plants. So that was a transition of technology from wet to dry. Then further, dry process has to be a larger, because the cement demand was so huge, so huge. Either you have to put a lot of plant or you just go for a big size plants. So I will say there is a big leap in the technology in increasing the size of these plants. So today the size of the plants are up to 5 million tons per annum. That kind of size cement plant are having. And when I joined, the biggest size was 1 mtpa. So higher the size means you have to um, you have to have a higher storage space, higher for the raw materials, higher capacity of mines. Everything has to multiply by at least 4 to 5 times mechanically. Then yes, during those times, the most of the grinding was done by the ball mills. So vertical roller mills has come somewhere in between. Then there is a roller press technology which has also evolved. And today, from last 10 years, I will say that waste heat recovery system has also come in. So when we talk about any dry process cement plant, you see a lot of gases escapes, which has a heat value of around 200 degree to 300 degrees Celsius. Now, converting that heat into some productive thing is not very much possible. It was technically very challenging. So of late, this waste heat recovery came, and now this actually substitutes something like 10 to 15% of the power requirement of the plant, and That is how so by that much thing you can conserve the power. So this is how the today's cement manufacturing unit is there. So for a general understanding, when we talk about Portland cement, so what is a Portland cement? So if you when we talk about limestone, it is actually CaCO3. It's a calcium carbonate. So the moment we remove the CO2 from CaCO3 from the calcium carbonate, the moment you eliminate CO2, you get CaO. And in a typical cement, 60%, somewhat 60+% should be CaO, then silica, then alumina, then somewhat iron and magnesium, gypsum. And it is a very complex chemistry. Though it may not appear from outside, but it is a very complex chemistry because most of the mineral, when you mine bulk material or bulk mineral, there will be a lot of variations in the quality. The lime deposits will have different concentrations of lime, different concentration of silica and alumina, while our plant needs a certain band of so you require all the time corrections of lime, silica and alumina. So these are very important three things: lime, silica and alumina. And whosoever is in the cement industry, he very well knows that LSF, that is the lime saturation factor, is the only or is the one very important aspect of the process of their process stability, and in order to maintain the quality of the final product, they have to maintain the LSF. So all the material. Yeah.
Umesh sir.
हाँ जी बोलिए.
Excuse me, sir. So different brands of cement will have this composition only, or they do they have different composition also?
No. Same composition. Cement is actually I will say that it's a IS code material. So it's it is a we have to comply to the IS codes.
IS codes.
So IS codes is basically more on to the physical.
During the chemical process, you have to control, because you are getting raw material from different mines actually.
But the same mines, but in the same mines also there is a lot of variations.
Yes, surely.
Because there will be length and breadth of the mines, so there will be different concentrations, or it will have some variations, maybe 2% variation, 3% variation. So those people or those plants are very lucky who has got a very good and consistent lime deposit across the mine. Yeah. So they do not have to. I would say their complexity levels are much lower. So for
sir, you said it is heating, grinding, and then grinding, heating, and then again grinding.
Yes, it is actually grinding.
Where
heating.
This chemical controlling is done, sir? Where in between?
See, all the raw materials which are coming, it has to be grounded. It has to be made into powder state. Even the coal has to be grinded, and then it is heated. So while it is heating, the chemistry starts playing the role, because from the limestone, the CaCO3, the CO2 has to be removed. It is a reaction which has to take place in the presence of oxygen. So disturbance is coming, I think. Has some okay. So yeah. So LSF, these three are very important components of the cement. And when, as you, Singh sir, as you have asked me, all the cement has to comply certain physical I would say specification. So for maintaining those physical specifications, you have to have certain chemistry, and that's the reason all the cement, whosoever is the manufacturer of that cement, has to have that thing. So typically, if you say a very good branded cement and mediocre brand, the difference is only of the consistency. The better brand will have a consistent quality of product, while mediocre brand may not have that kind of consistency because they may not be using all those kind of equipments and control and the knowledge which needs to have all these things. They may be missing somewhere in that. So that is the only difference between good cement and not so good cement. Okay. Any other questions, or should I go ahead?
Please carry on, sir. We will ask in between wherever we feel like.
Feel free, sir.
Thank you.
So, so I will just take you through the process. So what I said, now I will try to explain you through this slide. So typically when we talk about the mines, so in the mines, you have to dig out all the limestone. So there is a machine called shovel. Shovel puts all the material in the dumper. Dumper dumps the material into the crusher. So there is a size reduction from the rock to through the crusher. We reduces the size of the material to somewhere between 70 mm to 20 mm. Now these material goes into we call stacker and reclaimer or pre-homogenization. From there, this material is fed into a raw mill. Raw mill is actually now converting this material into a powder state. Okay. Now this powder, as I told you, that there is there may be possibilities that whatever the material you are getting, they may not have the same quality band all the time. So there is a homogenization hoppers. So where we stock different quality of materials, and accordingly, if suppose my lime is coming down, so if I am having a sweeter in the second hopper, so I will dose little sweeter in that. So this is how we maintain the quality. So all this powder material will now go into this process, which is the heart of the cement process. I will say the 90% of the cement is this pyro section when we talk about preheater, kiln, and the cooler. So this section is the heart of the cement plant. So now this material is fed into the preheater. Now, as you are seeing that this is a limestone circuit, there is a similar coal circuit also, where the coal is grounded, and it is made it is pulverized, and then coal is fired in this rotary kiln from this point. Now this flame and this gases, whatever we are getting, so it is coming out from this preheaters. So this is where the heat transfer happens. And this material, while it is coming down the kiln, it changes the phases from CO2, CaCO3. It will release a lot of CO2. Similarly, the coal, when coal burns, it also releases all CO2. So there are two kind of CO2 which comes out of the cement process. One is from the mineral itself. The second is from the coal. Then this material becomes in the nodular shape, and this is undergone through a cooler. So cooler is basically to cool down this clinker because they are red hot. They are almost like a molten metal. So a lot of air is used, and this heat is again recuperated back into the preheater so that we utilize each and every aspect of the heat. And then this clinker is now fed into a clinker silo. Now this clinker which is there, it is again put into the cement mill for grinding, and after grinding and adding some of the things like gypsum, which helps in setting properties of the cement, and then the cement is sent to the packing plant where it is packed and moved to the destinations. So this is all about the cement process in short. While this diagram is showing a lot of ball mills, but today the ball mills are, I will not say that it's completely obsolete, but yes, now the new plants are not coming up with the ball mill because they are not so energy efficient as the vertical roller mill. So they all are replaced with the vertical roller mill. So now I will just take you one by one through those things. I think I've explained you about that how this thing works. in the mines space. Then so from the quarry phase, the blasting is done. The quarry phase, the material, the rocks will be taken to the shovel to dumper to crusher. Crusher will reduce the material size, and then it will be sent to the stacker and reclaimer. So now we are coming to the storage at plants. Now it is again put to the raw mill. Then raw mill, and then in this diagram you will see. I was talking about the cooling. No, so the flame, the coal, what is being fed is fed from this side of the kiln or from one side of the kiln. This hot gases is now doing the all the kind of heat transfer. So now this hot gases will pass through this preheating strings, various strings, while the material is fed from the top of the preheater strings. So as the material comes down, this hot air will go out. So this is where the heat transfer takes place. So the material is coming down, it reaches in the kiln, and as it goes nearer the kiln, the material attains the temperature of something like 1400 degrees Celsius. And between 900 to 1400, this clinkerization happens. The phase change happens. So if you get a chance ever to visit a cement plant, you do see the nowadays they have a closed circuit TV also, so you can see that how that nodular clinker is formed. You will be able to see that how this material melts down, fuses like hot syrup, and then they will form the nodular clinker, and that will fall in the coolers. In the cooler, now it has to be cooled, so a lot of air will be blown to get this material cooled down, and this material again, so while cooling down, there is again a heat exchange. So this air is again recuperated back into another preheater string. There are two strings which we call kiln string and the preheater string. So this is how we try to conserve as much as heat as possible. And still I'll say that the theoretical requirement of the heat is still around 400 kilocalories per kg of clinker. But because our heat, because we do not have that technology, the best technology we have is still giving us something like 900 kilocalories. So there is still a, if going forward, I would say, if technology develops further, then possibly we will see some good thing happening in this particular area. And this is the area which is generating all the CO2, all the heat is. So I will say this is something like 80% of the cost is this area only. So these are some more pictures for you to understand that how does the kiln looks like, and the internals look something like this. This is how the material turns into red hot clinker. This is another diagram which is just trying to explain you that what are the phases of as the material comes down, it just releases the moistures, then preheating, then pre-calcining, then this is calcining, sintering, and then cooling.
Okay. Excuse me, sir. May I ask a question if you allow, sir?
Please.
Sir, is there any method or technology have developed to restore or to use the already used cement or concrete to make a clinker of that? मतलब can be like जैसे कोई cement बन गया, कोई concrete बन गया या कोई cement बन गया, can I reuse it in some way? Is it any method or technology so far developed, sir?
No, see, the thing is that again, the whole art of making cement is the consistency of the raw material. So if you recover, if you are getting a cement, then it can be regrinded and dosed to certain quantity back in the raw material. That can be done. I'm saying theoretically and practically also with certain proportion it can be done. While if you talk about making of a concrete, it is another ball game. I will come to that part later. In the later part of my slides, I am covering that aspects also.
Thank you, sir. Thank you, sir.
Right. No. I will just because we all are engineers here, so I will try to tell you something about the paradox or the enigma here. That in order to recover more and more heat value, we need to have a it is good to have like infinite height of the kiln string or this preheaters, because as much as you get the length of the preheater, that much heat you will be conserving. But because of the construction limitation and you have to put the material on the top, so you already are incurring some energy to put the material over the preheater. So there is an energy cost in making this material dump over these things. So there is a cost of that. So you have to make a technology balance that what kind of preheater is actually right for you. You can go say 4 stage, then 5 stage, then 6 stage. You can go to say 7 stage, 8 stage, and infinite way. But the moment you go increase the height of the preheaters, your material dumping cost is also increasing. That is also consuming a lot of energy. So you have to balance both of the things. So typically, the most popular things are like 4 stage to 6 stage preheaters are the most popular designs these days. Okay. So now let's come to the grinding part. So grindings. This particular slide is talking about some old technology where the ball mill and tube mill was used. Today we are having a roller press and a ball mill combination, and there are vertical mills also which are doing the finished grinding, because the particle size distribution is one of the important aspect of the quality of cement. So how many particles of which size, what percentage of particle of which fineness, so that determines the physical properties of the cement. So that is why grinding is, again, I will say, science as well as art, and the technology plays an important role. And today the technology has fairly evolved, and we have a lot many options. And this is the place where we also have to grind the clinker, which we have got converted from limestone. And while the other add bags like fly ash and slags, which is the waste of the other industries, are also used here, because they have to just get added into this ball mill or tube mill or roller press or vertical roller mills, and that's how this cement is made. So today in India we have got at least 3 popular I will say specification. One is the OPC grade cements. So one OPC means we are not using any add bags. It is only and only clinker which is grounded, and some amount of gypsum is added for the setting properties. So that is the OPC. In OPC there are 3 grades: 33, 43, and 53. Okay. Now there is another grade called PPC. PPC means if you are using fly ash as a substitute, and to the degree of say 25%, then we call it PPC, Pozzolana Portland Cement. So Pozzolana was a name given, came from its European thing, because there was one discovery happened that the volcanic ash was showing the properties of cement, and that village name was Pozzolic or something. So that's how this name has come. So PPC is the second popular brand of cement which is in India. Third is the PSC. That is a Pozzolana slag cement. So whenever you use the slag from steel industry and that is mixed with the clinker, that is called the PSC. So these are the 3 popular grade of the cement. Apart of it, there are many more grades of the cement which is used for the specific purpose, like IRST or a sulfate resistant cement. So there are further more varieties to it, but these are the most popular thing. And because PPC and PSC, they are using the materials from waste materials of steel and power industry. So environmentally also it is very welcoming thing, and industry also encourages these products more because of the economic reasons, for the environmental reasons, and for general sustainability of the overall man. It is better if we use PPC or PSC. OPC used for some critical structural needs. So while I have covered most of the cement, but I tell you that cement is a still intermediate product. Cement is not a final product. The final product is concrete. So while most of the developing nation they have a practice of like making of cement, and then concrete is made in various location in the form of site mix concrete. So now in the I mean, say if you see a developed nation, this business is already fairly evolved. While in India and other developing nations, this is in an evolving state. So off late, I mean, say some 20 years back, ready mix concrete also or mechanized concrete making has also came in India, and if you want to know, it's actually what is concrete. Concrete is a mix of, let's say, cement with additives, water, fine aggregates, coarse aggregates, and certain admixture, and then concrete is formed. And you can directly pour the concrete for the structures. So the moment we use concrete directly into our construction needs, we improve the quality of concrete. Number one thing, I mean, so we get a better control on the quality of concrete, the uniformity or the homogeneity of the mix, and the property of concretes also. And also the wastages are reduced, and because everything is happening mechanically, so somewhere you are also saving on the labors or manpower cost. So this is a new evolving industry in India, and I will just take you through some more things about it. Yes. So when we say that how other countries are, how they are having the presence. So those who are cement manufacturers world over, they are also into concrete. And there's the reason why Ultratech in India or my company in India has thought that we should also be in concrete space, and we are also getting into it. And today we are a part of being the largest cement manufacturer, we are also the largest concrete players. And I am presently I'm working in that concrete industry only. And today, if you see all the countries like UK, it has a 52% of their cement goes into the ready mix concrete. Germany, 51% goes into the ready mix concrete. USA, 72%. Malaysia, 60%. Thailand, 30%. Indonesia, 20%. While India is in India, the cement which is going into the concrete or RMC is only 10%, or it is even not 10%. It is between somewhere between 8 to 10%. It is approaching that. It is trying to approach that 10% level. So there is a huge upside opportunity in India when we will be using more of a design concrete and the mechanized concrete. So typically when we talk about, so I have taken you through the process that what cement industry is, how it is spread it across India, and what are the challenges in making it. Now it comes that where does the cement goes? So if we see in India, these are the three. We define our customer segmentation into these three areas. So 20% goes into infrastructure, 32% goes into industrial and commercial, and 40% goes into the residential. So when we talk of, say, RMC type of setup where the concrete is sold to the end customer rather than cement, then typically, these infrastructure and industrial, these are the areas where it is used more than the residentials. So this is all about the market segmentation. I will also touch upon some aspects of the environmental aspects. And I do not have a detailed slide on this, but I will try to just put on what I know. from some of my notes. I'll tell you one important thing about this. That today we all talk about this CO2 emission. So cement industry contributes around 5% of the total global emission. So it's a very high. I think this is the single industry which is fairly responsible for a lot of global emission. But at the same time, we don't have any answers. We have to have we need to have our houses, we need to have roads, and we do not have any substitute material as of now. So the only thing we can now think of that how can we reduce the impact of the other contributions. As I told while going into this process part, that this industry is the cement. We are getting a CO2 from two aspects. One is while we burn the coal, and the second is from the CaCO3, the conversion of CaCO3 to CaO. So that is one thing. The mining, which is also a part of the cement industry, has various issues related to, say, forestation, vegetation, depletion of the topsoil, then water table disturbances. So these are the important environmental aspects. Though the responsible cement industry take due care of it, they all have very planned means and methods. They all have a visibility of, say, at least 5 to 10 years that what are they going to do next, so that nothing abrupt happens in between. But yes, these are important environmental aspects of this industry. And a part of this thing, dust is also emitted. However, this is where a good cement industry and not so good also gets differentiated. Typically, a good plant have got all the dry scrubbers, and they have a very limited. It's a particular distribution is very, very limited. Is reduced to a very limited quantum. And the other aspect is the lot of coal is used in making of a cement, and because of the coal, the energy efficiency is also an important aspect. I mean, say, better the energy efficiency, you can reduce the quantity of coal. The moment you reduce the quantity of coal, that will result into reduction of CO2 emission. Then efficient logistics, then water conservations. They are also important aspects when we talk about the cement industry. That because after all, industry will still require a lot of water for running their equipments and processing various aspects of the process. Like if you are operating on DG, you need water for as a coolant. The water is used to cool the bearings in various locations. So there is a significant amount of water which is being consumed. So that is also one aspect. Then efficient logistics is very important. That as I told you earlier, that the cement is a business of actually a logistics. You have to see that how the limestone takes the shape of your house. So that journey, how efficient you can make it, is all about the business. And then the good part, I will say, is that this is a digester of the other industries waste like fly ash, slag, iron ore, gypsum. If you see, we require something like 1% of iron ore. And this iron ore is generally sourced from the steel plants where for those iron ore which they are unable to use in their thing. They generally reject the fine iron ore. So that fine iron ore is used by us. So that way we are able to, the cement industry typically able to digest the waste of the other industry. So this is all about the environmental aspects. So the people management, and I want to highlight one more important thing, that cement industry itself is a confluence of the people from all the disciplines. All the discipline means we require mining engineers, we require geologists, we require electrical engineer, we require mechanical engineer, we require forestry people, we require sociology people, we require HR, I would say all walks of life, even the advanced analytics, science, chemistry, rural experts, government, logistics. You talk even the shipping, even the ocean shipping, the jetty, the port. All those management people are required to run this complete industry. And these days, even the washery is also has become a part of the cement industry. So whatever the coal is coming from the coal mines, that is washed, and good part goes to the cement, because cement process is highly dependent on the good quality of coal, and the little the second grade goes into the power plant. So this is how the cement plant operates. It requires a lot of means interdisciplinary people to run this business. Even significant quantity of cement is being exported. A lot of imports is happening. So we require the people who are experts in export-import management. Then research and development thing. So as I told you that while going through the process slide, I was telling that the pyro is one of the very important aspect of the cement industry. It consumes, I will say, the 90% of the cost which we incur in making of a cement is incurred only in that pyro section, where we are heating the material and making the clinker. And 90% of the emission, 90% of the heat is being used, or energy is being used in this section. So that needs possibly, I'm saying, the work is already going on, and there looks a possibility also that going forward, if we can bridge the gap, because the heat transfer is something, if we can improve on it further, we will achieve higher this energy efficiency levels. Then the grinding technology has also evolved from like ball mill to vertical roller mills and the roller press. Then particle size distribution. A lot of research work is going on the particle size distribution, the nanotechnology. There are some nanomaterials which can dramatically change the quality of cement, or it's more into application part. But yes, that is still that is a very promising area into that in this complete gamut. Then testing. When you are using a lot of minerals, you also require, so sample testing may not be the best thing to do, or sampling may not be. So you need something which can give you more depth of data, that whatever the batch which has passed, the total like lime content of this batch was total so much, not based on one discrete sample. It should be a larger sample, or it should speak. It should be more representative, so that you can have a better process control and the quality control. So there are gamma rays and XRDs. These are the equipments, and there are further evolution in these areas also. Robotics is also one of the aspects. In particularly cement labs, robotics has been used in some of the locations. Then artificial intelligence, deep analytics, because the chemistry and how the chemistry is, getting represented in the physical property. So there are a lot of unknown things. So deep analytics and AI also helps. 3D printing is also a new thing where research is going on, and we may see that if not our houses, but yes, some of the civil structures, or that can be made through 3D printing. And a lot of work, a lot of R&D work is going in the concrete space, because when we say concrete, cement is one. But from one cement, we have got 1100 types of concretes. We have 1100 codes of concrete in our company. So you can understand that how customization, what kind of customization is possible from the same material. So there also a lot of research and development work is going on, and if you ask me about the substitution, it is a very challenging thing, because today, if you see the cost of cement, it's only 5 rupees kg, 5 or 6 rupees kg. So you may not find any metal which is as cheaper as this. Means stock of anything. Everything is. This is one of the cheapest materials. So the substitution has to be, has to be cost effective. So we are still, or the complete mankind is struggling that how can we find better substitution of cement. So still that struggle is going on. There is one work which has been done by Dr. Davidovitz, who is a Canadian chemist, and he has came out with this geopolymer concrete. So he's talking about that instead of taking the limestone and heating it and making it clinker and doing all those things, the directly alkali activation can help you to make the concrete. But the moment now the problem here is that the alkali itself, making of an alkali is also a very environmentally challenging process, because the most economical alkali which is available is the NaOH, sodium hydroxide. So making of a sodium hydroxide releases a lot of chlorines also. So unless we have a down chlorine line or usage of chlorine, we may not be able to do it in a significant size. So geopolymer is one answer, but it is having its own related issues, and it is struggling. And we don't see that it can replace a substantial size of the cement. It may have an impact of to the extent of maybe 0.5% to 1% at the most. So this is all from my side. So thank you for patient listening. And if you have any questions, please you can put it to me.
Hello.
Yeah.
I have one question, sir.
Yes.
Yes,
So if there is a questions, I can take those questions. Are we in time or? I think we have.
No, sir. We have time.
Is it so?
No, sir. Yes, sir. We have time. So we have.
What is the range of particle size of cement powder? What is the range of particle size of final developed cement powder?
Actually, we don't see that as a range. Means it is again a particle size distribution. So it is a small. It has to be a curve which ranges that how many percent should be below 100 micro mm. I think it's 100 nano mm. I'm not very clear about. I may not be able to answer you very specifically, but if you given a chance, I will send you separately, sir, about this particular aspect. That so it has to be in certain range, and how much fine and how much coarse is also has to have certain balance to get the right physical properties. Both the things are important. That's the reason the grinding technology, how much things are grinded where, is also plays an important role.
Okay. Yeah. What's about sintering? Sintering temperature?
Sintering temperature.
How sintering is done?
So what happens? Sintering is a process when this mineral converts into the clinker. No, that is the sintering process. When the I have mentioned you. In fact, I can take it back to that slide. This is the place, or I will even take you through this first slide. I think this will give you some kind of visibility. See, when I talk about the preheater, this is the preheater, sir. Okay. So this is say 6 stages preheater. So material is being fed through these pipes which you are seeing. It is fed over to this thing. So now this material will come down. It will release the moisture, then it will get preheated, and then it will get partially calcined. And then I will take you to this slide. From that point, it now reaches to the mouth of the kiln, which is a rotary kiln. It's a big shell which is rotating in its axis, and a flame, heat is being produced through a flame. Now this hot gases is going from this area. So this material, while it is coming down, now here it changes the phase and it gets sintered or calcined, I will say, and it changes the phases from a powder to a molten metal type of thing. If you've seen a steel industry, you see that hot steel, a hot metal. So it almost looks very much similar to that. Something that is visible in this particular slide. So this is where the sintering happens, and when sintering happens,
What is the temperature range for sintering?
So it is 1500. It's around 1500 degrees Celsius. It's like 900 to 1500 degrees Celsius is the place where this sintering process happens. So when we talk about 1500 degrees Celsius, then it is the tip of this flame. It is the tip of this flame. While there is a temperature differentials across these places. So 900 to 1500 degrees, this sintering process will happen.
Okay, thank you, sir.
Yeah, right.
Sir, why the production of cement in developed countries like US very low as compared to India? Is it because most of the construction work is over there?
Actually, I would say this is the rationale, and I actually missed to tell you one more point that while we talk about cement, the per capita cement consumption is also very important metrics. So while US is having a very less population and their cement consumption is around 80 to 90 million tons, and that per capita, I think they are somewhere around 800 to 1000 kgs per person. While in India, because of our huge population, and we are even consuming 300 million ton of cement, our still the per capita consumption of cement is only 200 kgs per person. So there is again a huge upside. That's the reason we are talking that in India we will actually in next say 10 to 20 years we will certainly graduate from this 300 level to something like 800 or 1000 level, and then possibly after 20-25 years the saturation may happen, and then demand may further come down. But as you said, right, yes, they have done a lot of consumption has already happened. They all are having a very good roads, all airports, and all the infrastructure is already there. So their present consumption is not very much. In fact, it has improved a bit in last 4-5 years, but before that it was very low. In fact, most of the American cement companies were bleeding because of the glut in the market.
Sir, after the introduction of the cement roads, concrete roads, what is the change in overall consumption and production also? Is it something visible at your end?
Yeah, because as I told you that around 30% or more cement is going into infrastructure, and yes, concrete roads are very healthy for the economy. I would say it has a very long life, so our life cycle cost is also low if we go with the concrete roads. Repair cost also reduces down, and it helps to have a like uninterrupted traffic, and even if some repair is required, it can be done very quickly. So these are some of the benefits of the thing, and yes, because of the concrete road introduction, yes, cement consumption is seeing a good consumption on this area also.
Okay, sir. Thank
you. Sir, dear Umesh sir, I have two questions. First question is like for entire global warming is about contributing 2% of the cement, sir. What is the as you said, what is the alternative material instead of cement? And second one, I mean, what is the best way to reduce the cement content for the concrete, or any alternative or something?
Yeah. I think this is a very, very good question. Very good question, and very close to my heart. So, when we say that cement contributes to say 5% of the total CO2 emission And CO2 is the like when we talk of the global emission, CO2 is every emission is converted into CO2. You know, all the house gases are converted into CO2 equivalents. You know? So 5% of the total emission is coming from the cement industry, and we are, as of now, we are not seeing any good substitute of cement. There are substitutes, but then they are very expensive, so they cannot be applied to this quantum as now. What are the alternatives? How do we control this thing? So the first way to control will be, so these are, I will talk about the levers. How should the cement industry react to this response?
Right.
So first is that let us start using more and more the other industries waste, like fly ash from the power industry, from the thermal power industry, whatever the fly ash which was becoming like landfilling issue. So why not to use it as an add back in cement? Then slag, the slag is also get wasted. So why not to use more and more slag, more and more fly ash to be used in cement? So this will help you in reducing your CO2 emission, because if even see, this can be used to the extent, slag can be used as high as like 50 to 60%. So to that extent, you can reduce the impact of the global warming, I will say. The second is the fly ash that can be substituted to the extent of 25 to 30%. So these are the two big levers. Then the third lever will be that can we reduce the energy intensity in the cement? So can we use the agricultural waste instead of coal all the time? So so there are all the cement plants are actually working on these areas. So depending on the availability of the agricultural waste around their locality, they substitute to some extent. So agricultural waste, municipal solid waste. So the moment these things are used, so you are reducing the CO2 which otherwise would have come from the coal. Then waste heat recovery. So whatever the gases or hot gases you were rejecting at say 300 degrees Celsius. So if you are converting that into some kind of power, which is substituting your power by say 5 to 10%. So that is also having an impact on improving your energy consumption down. So these are some of the important levers which cement industry is exercising, and they have to exercise for the sustenance of their industry as well as for the mankind also. So I hope I have answered the second part of your question, but the first part was that do we have any substitute? We are still struggling for a good substitute at a cheaper, at an economical cost. Whatever we are getting, that recent thing which is a geopolymer concrete or geopolymer cement, that is having a different kind of environmental issues. So it's like is it good to have to release CO2, or it is good to release chlorine in the atmosphere? So that is the question where we will be struggling.
Right, sir. Thank you, sir.
Thank you.
Hello, sir.
Yes.
Adding fly ash or slag 30% in the cement. Is there compromising in the quality of cement? Is there?
No, not really. No way. It cannot be done. See, because we are having that IS standards, it has to meet those physical properties. Those strength criteria have to be met whatever you do with whatever fly ash you are using, but then you still have to meet those criteria. So that's the reason we are not at all compromising with it. But instead, I tell you, there are certain benefits of adding fly ash and slag. Whenever you make a concrete with using the normal cement or OPC, a lot of heat of hydration is released. So while casting the concrete, because of the heat, we see a small micro cracks coming in the concrete. So that deteriorates the quality of that civil construction. So with addition of fly ash or slag, they reduces this heat of hydration. So in a way, they have got two big contributions. One is that they don't compromise on strength, because they have all the elements of the cement which should have, except for the lime. They are less in lime, otherwise they are as good as cement. Fly ash is nothing less than cement except for the lime. So once it is mixed with cement, it gets lime from cement, and that overall thing becomes very positive for the construction.
So there is no change.
So
Ultimately,
we are not compromising with the addition of slag or fly ash. Yeah.
Okay. Thank you.
Sir, how many type of tests to be done before the finalizing?
Yeah, can you come again? I could not listen your question.
Sir, how many types of...
I think voice is not clear, and there is some disturbance. Can you come again, please?
Sir, could you repeat your question, please?
How many type of tests to be done before finalizing the cement?
Oh, how many tests can be done? See, actually, in order to get the adequate quality of cement, each and every stage. So when I talk each and every stage, so we start from the mining, that which rock to be mined, which part of the mining has to be done today, and where it has to be mixed. Each and every places there is a sample testing is done. We get to know that the chemistry of that overall mineral, and then that is fed. And in each intermediate stage, the test is done to understand that whether everything is falling in that particular quality band which we want to have the process stability. And similarly, so there are a lot of, I will say that if not, there are at least hundreds of tests which is done daily in order to give you a cement which should meet the specification, or what we say, it should suffice that quality parameters.
Sir, can we use sugarcane bagasse as a cement substitute?
Sugarcane bagasse can be used as a fuel, substitute to fuel. So
no,
when
like we use fly ash or slag. Likewise, can we use that in cement to replace cement partially?
Sugarcane bagasse, bagasse is basically a fuel, no? I mean, it's the waste of the sugarcane. So, or are you talking about the ash generated from the?
Yes. After burning that sugarcane bagasse, whatever the ash generated, that can be used.
That can be used, but one thing which is a point of caution is the carbon content, because the ash which is coming from, say, NTPC or very good power plant, they have a very low carbon content, while the bagasse, the kind of boilers which the bagasse burning is done in, they do not have a very adequate process control, and lot of carbon particles are there. So to answer your question, if that ash is having something like 2 to 3% of carbon content, yes, that can be used very easily. But if it has a carbon percentage something between 3 to 5%, then also it can be used by mixing the other ash. But if it is more than 5%, then it is difficult to use, because that will be detrimental to the cement quality then.
Okay, sir. Thank you, sir.